to our second virtual meetup, all about building reliability and data evolution. I guess just a little bit of background for people that didn't attend the first one, behind obviously the virtual meetups and Data Republic. So myself and my colleagues at the Republic founded Data Republic this year as a place for data professionals to share their knowledge and network with peers. This evening we're joined by Oliver and Sergey, both incredibly experienced and successful data professionals. I'll pass you over to our first speaker, Oliver.
Today I want to tell you a little bit about Kolibri games and how we basically, our history with data and how we kind of started out and then progressed and basically want to tell us you also like where we stand now. Yeah, so quickly it's about like what Kolibri is and what we're doing. So we founded the company back then, about like for almost 5 years ago, in Karlsruhe, which is like a smaller city in the southern part of Germany. We were working from our students' apartment back there, trying to develop some games. So you can see my other co-founders, and I'm the one with the back towards you. Yeah, so we started out there, wanted to build some games. We're straight out of university, or basically still in university, and just tried that out. 2017, we had like a small team already, and but back then we decided that we want to move to Berlin. So we basically wanted to grow our company and attract more Kolibris, to have a more international surrounding, and to be closer to industry partners as well as like investors and so on. We never needed any money from investors because we managed to do it to bootstrap it, but it was still good to kind of be in that place in the case we would need any money. So we moved there to Berlin with around 30 people back then, and then in 2018 we achieved our first success, where we reached like our 15 million downloads for our games. In 2019, then our efforts paid off. We basically scaled within a few years to around 100 Kolibris and also like over 100 million downloads. Since 2020, we are part of Ubisoft, and now can basically with Ubisoft we can try to get they can help us to achieve our goals better and to become like a world-class gaming company. Our most successful game is Idle Miner Tycoon. You can check it out in Google Play and Apple App Store. So we are mostly only building like mobile games and actually focusing on the idle genre, which is a gameplay or game genre where the game also plays itself when you are not in the game. So what you can do in the game is like create mines, unlock new mines, increase your income, and till date we are having over 150 million downloads. Now I want to tell you a little bit like about our data evolution and how we progressed with the data stack, what were our needs, challenges, and learnings, what we did so far. So in 2016, we had like the first needs for data immediately after we launched our first game. We basically wanted to know is our game working? Are users playing the game? Are we making any money? So we basically want to establish some kind of basic business reporting in order to see if we should continue with the game, if we should build a new game, or if we want to double down with the game. So our objectives were like to report in-app purchase revenue. So our game is monetizing with in-app purchases as well as with ads. So we want to get to know like how much money are we making with in-app purchases, also with which in-app purchase are we making, how much money. We also want to get to know if people are watching ads, how much ads they watch and how much revenue we are kind of generating out of them. Then also wanted to know if like our game is running in a good environment, and if we introduce any bugs or crashes in there. And also report like game specific KPIs, more like retention, how many sessions, how far in the game the people are. And yeah, these were the things we wanted to achieve in 2016. So we were a small team back then, kind of only us founders and some interns, but therefore we couldn't build up like our own kind of tech stack. but needed to rely more on third-party services. So we integrated Facebook analytics, game analytics for kind of in-app purchase reporting, also in-game reporting, and also Firebase Crashlytics, which was back then not part of Firebase, but from Fabric, which is more independent, but then got acquired by Firebase to report like crashes, bugs, and so on and so forth. And also like we had multiple ad partners, which had dashboards kind of showing the KPIs and revenue we were making. So we had like these 4 locations where we could go into and ask any or answer any questions we have about these topics. But there were a lot of challenges back then. So as you could see before, like there was not one place where we can take a look at everything. So it was kind of, if we want to know like how much money we are making, we needed to go to Facebook analytics, to Google Play Console, to the ad revenue partners, and also we always needed to integrate like some SDKs into the games, and there were like a lot of problems with these SDKs. They're kind of sometimes not really working together. Sometimes you need to do some workaround, and that was not really good for us. And the reporting between the SDKs also differs, since they often like define certain high-level KPIs differently. So for example, like retention on one dashboard was way worse than on another dashboard, and then we didn't know like who should we trust, how they're actually calculating these things. So there was like also like a lot of missing transparency. And then it was also like hard to dig deeper into the data, since we only send events through these SDKs, but there's no way for us to access this raw information of kind of, okay, the retention is X, but why is it like that? Or users are dropping off at a certain stage, why are they kind of dropping off? And it was not very, very flexible as well. So in 2017, we also then started with performance marketing. And luckily, we kind of had a lot of organic downloads in the beginning, so we didn't need to start with performance marketing from the beginning. But then kind of it became agreement that we want to have more users in the games, and also like see like if we can generate any profits out of that. So because we are bootstrapped, we all already wanted to have only profitable campaigns, since we didn't have like a lot of money which we could invest into these campaigns. And it was very important that we do like performance marketing and really looking at if we are getting more money out than we put in. So our objectives were that we want to first calculate return on ad spend. So basically find out like if we spend any money on any campaigns, how much money are we getting back at which days in the lifetime of the players. And therefore we also needed like a simple user lifetime value prediction to basically identify early if the users of a campaign are profitable, because if we wait like 30, 60 or 90 days and see like what the lifetime value of the user is, it will take a long time, and in that time we can't make any decisions if we should spend more money, spend less money on the campaigns. And therefore we did like some very simple predictions. And we also built up a kind of bidding algorithm which helps us to identify like which campaigns are running, what is the expected ROAS, what is the expected LTV, and how much we should bid on these campaigns in order to get to a profitable stage on the campaigns. So back then the team was kind of only one marketing manager, which kind of did everything, like also build up the script to the bidding algorithm, did the calculations, and set up this whole thing, managed and optimized the campaigns. So he did it with like AppsFlyer and in an R script. So AppsFlyer is like an attribution network. Basically, it helps you to identify where users came from which campaigns they came into the game, if they were organic users. And this is basically needed to identify like, okay, these users are coming from campaign A and making that much of revenue after X days. And then we can basically see, okay, if this is profitable or not. And so he kind of had like this R script written up. It was like back then very hacky a thing with no version control. It was running locally on his computer, and then this R script kind of put back the scripts to the UA channels, which then report again back to AppsFlyer where the users basically came from. So challenges here were like that there was a lack of transparency. As I mentioned, like there was only this marketing manager, which was very talented and did a good job, but we didn't knew exactly what he was doing. So we needed to trust him, and we saw at least like in our reporting that it was going in the right direction, but we didn't knew anything about that. It was also like sometimes a little bit error prone. So if he did any mistakes, the bidding algorithm kind of generated different results and or unwanted results, and there was no real version control. We started at some point to save it into Dropbox because it was the easiest way, but of course this is nothing for a professional development environment. And though we introduced now also AppsFlyer, the data was even more scattered. So we had like data in AppsFlyer, we had data in all the other third parties, and was actually getting even worse. So our goal in 2018 was then to centralize more the data and professionalize the performance marketing. So we wanted to have like one tool to gather all the information. We often called it like kind of brain of Kolibri, where everything gets put in, where we can take a look and combine the data, and also have the transparency so that everyone can have access to this data and can take a look into things. Also, we wanted to be able to deep dive into data, as was mentioned before in 2016, that there was no real way for us to dig deeper on why certain things are happening. Can't really track the user behavior over time. So we started to invest, or like basically we wanted to make a decision if we want to go with any other third-party software, kind of try to get everything somehow in there. There were some paid solutions for that, but then we kind of decided to invest in our own solution, and therefore we could then like be most flexible, but it was also like kind of the most work we needed to do. But we thought like that's kind of only the way if you really want to get to a more data-driven business. So we started to collect the raw data by sending events from the game to kind of our backend, built a central data warehouse, and set up dashboards in order to see all the KPIs and analytics we wanted to do. So the team back then grew a little bit. So on the marketing side, the one marketing manager in the beginning who did everything kind of got promoted to the marketing director, did hire some more people, some marketing manager, including one marketing analyst as well, who then continues to build up like the dashboards for marketing. And we also hired 2 data engineers in order to set up the initial tech stack I was referring about for our own solution. And this is how it looked like in the beginning. So we were on the Microsoft Azure cloud before with some other services, and therefore we worked closely together with Microsoft on building up a tech stack as well in order to have like these analytic pipelines set up. So I quickly explained each individual tools, since they are very Azure related, but there are some things which are also like similar to some open source tools. So first the game sends some events to Event Hub, which is kind of event distribution similar to Kafka or Kinesis. From there on, we stream the data with Stream Analytics into a data lake storage, where it's kind of the raw storage. Then we have a data lake analytics, which is an Azure tool to kind of do data transformations. And later we put them then also in the SQL database, which is then connected to Power BI, which is like a dashboarding tool. So we also integrated, so most of the analytics providers we had integrated already back then, had some APIs. So we also used these APIs with some Azure functions, which are kind of on the AWS space, it would be Lambda functions, put them into the data lake storage as well. And then that everything is kind of accessible from there, and then we put everything into the SQL database in order to access it via Power BI. We used Data Factory back then, which is kind of scheduling orchestration tool from Azure itself to orchestrate some jobs in order to move the data, transform the data, and so on and so forth. So later we decided to remove the Power BI dashboarding system for Looker. Looker has this functionality that they also like having this LookML language, which allows for basic data modeling, and also for people who are not so familiar with SQL, that they can set up certain dashboards, can work on data models, and so on and so forth. So this was also like a big step forward. So some challenges for us back then were the query performance. As you saw before, like we store everything in like a SQL database, which was not very suited for the use case actually, but back then we didn't know better. So this was having some really hard times, I would say. So it was also not very stable and reliable. There were often like jobs failing on the database. There were like a lot of if different users kind of access the database, the query performance dropped even more. So if some users are working on some dashboards or looking at some dashboards, there and at the same time there was like some job ingesting data into the SQL database, it kind of dropped, and it was like kind of always like an up and down, and not really stable. And we needed to spend a lot of time to keep the system alive. So we needed to take a look into jobs, or like lot of jobs were failing. We always needed to work on indexing, and it wasn't helping at all. So in the very beginning, the SQL database was okay for use cases, but when we grew to more users and got more data, this was just not scalable anymore. And this was back then a huge problem. So in 2019, we wanted to get more into like kind of data oriented. So we wanted to create like real insights for our games. So we want to build up deeper dashboards for our games. So back then we only had like very high level reporting. We want to run our first A/B test, which we didn't do until 2019, and improve the tech stack to overcome the challenges I was just talking about. So what we want to build up is like a monetization dashboards, which is like way deeper than just like the high level KPIs. So we have like certain offers in our game. We have a shop where we sell like goods, and we have ads, and how much do we earn with each of them, which is performing well, which is not performing well, and so on and so forth. Then a progression dashboard, where do our players drop off, also much deeper than we had it before. Engagement dashboards, kind of retention and interaction with the feature, with which features are the users interacting more, which features are the users not so much interacting, and how much kind of time spent is on them, and if they're working or not. And of course, like to improve the performance and the stability of the whole technical system. So for that, we needed more people to make use of the data and build these dashboards I was referring to. So we hired like a head of game data who is taking care of building up a team which is more focused on the analytics side and really making sense of the data, and kind of find out how we can actually use the data to also drive the business value forward. Before that, we had got a technical system, and it was very much used for marketing, but we didn't use it so much for the game itself. And we also hired 2 more BI developers, which in our case are taking care mostly of building dashboards and kind of building up data models to support the dashboards. So this is how our tech stack changed and looked like in 2019 then. So we exchanged certain modules or kind of systems with Databricks and Spark. So the infrastructure is still running in Azure, but Databricks is kind of a third-party service which can also be run on AWS. And but for us, like, this was like a more scalable solution, and also like you can run what kind of Databricks runs Apache Spark, also like kind of an industry standard for these kind of things. So instead of using the stream analytics as I was showing before, we are now using Databricks Sparks for streaming the data from the Events Hub to the data lake store. We're also now ingesting data from the partners via Spark, or also like Python scripts, which you can also run on Databricks. And then from the data lake store, we kind of have the Databricks offers kind of a notebook feature similar to Jupyter, so where we can run like some Python scripts or do some R calculations, which some people kind of needed for their work. But we are still ingesting like with Spark to the SQL database. But we also did then some more changes in the stack. So we changed Data Factory and the SQL database with Snowflake and also Databricks. So with Databricks, you can also schedule analytics jobs. So we had like this one unified platform where we can do most of the things, and later change like the SQL database for Snowflake, which kind of had like overcomes like most of the challenges we were facing back then. It was much more stable. It scaled. They have like a multi-tenant feature where like dashboards run on one cluster, ad hoc queries run on another cluster, ingestion jobs run on another cluster. This helped then to kind of get rid of these problems we had before. Also, it was much faster out of the box, so didn't need to work on any indices, and was just like ingesting the data, and then it was kind of available with fast query times. There were still, of course, some more challenges. Like now it really became like, now that we had like kind of the technical stack was kind of in an okay state, I would say, but we needed to find out how we can really utilize our data. We were running some A/B tests back then, but they were also all kind of be run in a single script from our head of data, and then presented to us, but there weren't any dashboards. There was no automation behind that. And it was always like a very manual process, and therefore also transparency was missing. And then we actually had this data, we had these dashboards, we were building up all of these things, but for some reason we didn't use that data so much to drive our decisions. So we were still very focused on our intuition, on building the games, and also like a lot of community feedback, but the data was more there for reporting, but not really kind of driving our business forward. So then we kind of started the project, which we called Data 2020, and basically wanted to get ourselves more data driven. Our goal was to make our decisions fully data driven and to unlock our game's full potential of that. So we set our goals as that 90% of all our decisions on Idle Miner Tycoon, which was back then also our most successful game still, need to be backed by data. The time to insight for all data-related questions need to be smaller than 1 hour for 90% of all the questions, and 90% of all changes need to be validated with analytics. So we want to make decisions for almost all our decisions should be backed by data, but then we also want to validate almost all of our decisions afterwards if like we had like the desired, or like if certain changes in the game have the desired effect. And we thought it was very important that we can have like a fast time to insight for these data related questions, because like otherwise people get frustrated, and the longer you need to wait for an answer, the less useful the answer will get. So we kind of set these goals, and also hired then a lot more people around it. In order to establish these goals, we wanted to focus on 4 initiatives, which was personalization was very important. So we wanted to kind of use the data to then better identify like which segments of users it's better to which type of users certain configurations are working better for the game. So example, like we had a shop, but there were like some very expensive items in the shop, which like someone who didn't convert to a payer wouldn't buy either way. So we would rather like show them a more specialized shop in there. So we wanted to do more A/B tests. I was telling before, like it wasn't very transparent back then. There wasn't the ability to run a lot of A/B tests, since it was a more like kind of manual process. And as our goal was to validate most of our decisions, we wanted to do that with A/B tests. Third initiative was insights. So we wanted to get much more insights in order to make these decisions data-driven. And we wanted to work on predictions so that we can better predict like the lifetime value, predict like churn, when a user will churn out of the game, and use this information then to also adjust the game in certain directions. So here's again like visualized. I was already talking about most of them. So the team then grew quite a lot. We then kind of had for the first time something we called product analysts. So these are kind of embedded teams inside the products. And this was very important for us to actually so that they have actually the resources to answer their questions and don't need to be blocked by any other stakeholders. And they can work much closely together with the product managers and can therefore probably also much faster answer the questions. We had more data engineers in order to cope with like new challenges around like ingestion of more data and building more development environments. We had like an analyst in the data platform team as well, and hired 2 data scientists in order to help automating the A/B testing as well as doing the predictions. So this is then like how our stack kind of looks now. So what changed is like that we're now using Airflow for job orchestration. With Databricks, it was more like a scheduling tool. It was not so much an orchestration tool, but we needed like that in order to kind of chain certain jobs together, and was switching that out for Airflow. We are then introduced also DBT as a data transformation tool and also modeling tool for data. Looker was working quite well for us for a long time with the LookML language, but at some point it was harder to scale. We had like a lot of different logic applied in different places. So we wanted to centralize this with DBT. And we are using Databricks and MLflow for all our machine learning use cases. So, but there were still challenges. Data quality now is a big topic. More and more people are relying on the data. It needs to be accurate way more than it was before. And therefore we really need to work on these things now. The more people are also working on the whole stack, building up new dashboards, integrating more data and so on and so forth. So there was like a lot of errors and bugs introduced. So we need to now like kind of working on better environment for staging and production or testing, building up more unit tests, building up more end-to-end integration tests in order to make sure that the things we develop actually have high quality and not kind of ruining the data quality itself or the dashboards itself. Also, we think like personalization is still very important. We did some early steps there, but it's still also like a very manual process. What we do basically, we identify like certain kind of users, put them in a segment, and then kind of change game configurations on these segments. But we want to do this in a more automated way, where kind of some models are kind of finding out which users we should show which configuration in the game, so that we can really go down from a segment level to a user level and personalize the game experience for each individual user with specific game configurations. So that's probably what we are working next year on. Last but not least, I want to kind of also share some learnings. We decided at some point to build up on our own stack, and it was like kind of a huge investment. We needed more people for that. It took some time. There were like a lot of challenges, as I was mentioning, but I think in the end it paid off for us. I think like if we wouldn't go for an own solution, we would not be here where we are right now and wouldn't be able to fulfill all the use cases we want to achieve with data. then I was telling before, like, choose the right technologies at the right time for the right amount of data. So the SQL database in the beginning was working, but we guess dig too long to it. We should have earlier go to Snowflake or any other data warehousing solution. We sometimes also did some things in the opposite way. So we, for example, used Spark also for low amounts of data, and therefore it was just like costing more and was more overhead in general, where like a simple Python script could work out. So really need to think a little bit more ahead, like what are the right tools for the right use cases. Because like we had some issues with data quality and data transparency, there was always like losing trust in the data, and that's something I guess I would try to take a look earlier, to establish a pipeline which delivers high data quality in order to get this trust of the people. We also sometimes jumped into some use cases which we weren't ready yet. So we needed to get the basics right first before we go more into the data, advanced data applications. We started also out with like the whole analytics topic from an engineering standpoint. So I'm CTO, and therefore we were focusing a lot on the pipeline, technical pipeline itself. But we didn't thought so much about like how we then actually gonna use the data and how it can drive the business. And therefore I think like having analysts from early on can help into kind of having these internal stakeholders, which the technology team is working for. And I think that's one learning, that we hired them too late. And now, as I can see, also like we have kind of a technical system which is working. There's a lot more to do, but now it's basically the time to establish a data culture, and that's even more important than just building the stack. So these were my learnings through the 4 or almost 5 years now that I'm in Kolibri, helping building up this tech stack, helping to get us into a more data-driven way. When at least I back there looked at some blueprints, I couldn't find anything related to like how to set up proper data infrastructure, how to set up using the right tools. There were some of course articles and so on and so forth, but I thought it was like still very scattered, and I hope here I could at least like show you a little bit like how we did it, what were the challenges, what were our learnings, in order to maybe for your startup or for your organization to build up a data stack as well. So are there any questions?
Yes, I have one. Thank you for the talk, first of all, and sharing the insights. So how did you match the people who clicked on the ad, or actually for the ads you paid for? How did you manage to track the users in the game? Because sometimes I think people see an ad, click on it, and then search it probably manually in the Play Store. Mm-hmm. And then I think it's, and I don't know, did you track these users as well, or?
So how it normally works like is like from AppsFlyer, the tool I was mentioning, the attribution provider, they provide certain deep links. So if you click on an ad, you actually click on a deep link, which gets reported to AppsFlyer that you clicked on it. So this doesn't mean like that the user downloaded the game. So then there in AppsFlyer, you can kind of specify like attribution windows, which in our case is 7 days. So kind of when a user clicks on the deep link, it gets sent to AppsFlyer. And once they install the game in the time window of 7 days, then we would attribute it to that campaign. This, of course, doesn't often mean like that just because the user saw the ad and clicked on it was like the trigger to actually download the game, but it's like the best trade-off you can make here. And there's a lot more around that, which is very marketing or UA specific, which becomes then even more challenging, but it's kind of the idea on how we track these users.
How often do you run the ETL pipeline to ingest data into Snowflake? Have you considered a streaming solution for that?
So we are currently ingesting, some jobs are ingesting like on a daily basis, some ingest on an hourly basis. So for the hourly basis, we do this mostly for our marketing jobs, since they need more recent data in order to be able to make decisions quickly. We tried Snowpipe as a solution which Snowflake offers to ingest data in kind of a streaming way, and this works also quite well for us since we're coming more from the SQL database where this wouldn't be working. We then didn't migrate everything over, but that's something we are thinking about, like doing it for, next year, like to ingest basically with Snowpipe the data from blob storage inside Azure to Snowflake, which is then, I guess, like more like this streaming solution. Okay, then there's a question about like how do you align DBT and Airflow jobs? Is there a distinction? What goes where? Are there dependencies between them? So DBT can also, like, especially DBT Cloud can also like orchestrate jobs, but we are using Airflow since we also have some jobs running outside of Snowflake, basically ingesting the data into Snowflake, and therefore we wanted to have like one solution which could do everything. And so we kind of use Airflow jobs to orchestrate, or Airflow to orchestrate DBT jobs. So we're doing all the orchestration in Airflow. We don't try not to do any business logic or something like that, or make it as dumb as possible, and do all the business logic in DBT. That's the distinguishment between these two. I jump to the next question. Have you came across across data ops? I found recently the Data Kitchen, which talks about the platform. Have you come across it, as it is something I force my organization to look into? Yeah, so actually we read the same book just recently in our data team book club, as we call it, which was very interesting concepts in there, and it's basically what we want to adopt mostly like next year on. So these were the challenges I was speaking about, like that we don't have like a very good test environment, we don't have like a proper staging and production environment, we don't have like a lot of CI/CD systems in order to move things from testing into staging into production. We kind of don't have integration unit tests so much. We are slowly building them up with DBT, which offers like a good support for unit tests, but these are things we kind of take a look into from next year on. Then there was another question. Can you tell us more about how do you perform your A/B tests and where does this fit inside your stack? So the A/B tests are running on Python scripts, which are kind of Python notebooks in Databricks. So we are using data from Snowflake, and the Python script is reading the data from Snowflake, and then kind of does some calculations on p-values, significance, and all these statistical things, I would say, call them, and then put them back into Snowflake, and then we visualize them in Looker. So that's like how we do the analysis. For the scheduling and sampling of the users, we built our own service for that, which I didn't put into the diagram because it would get too crowded. But that's how we do that.
Perfect. Thank you so much for your talk. We'll move on to the next talk. So I'll pass you on to Sergey.
Thanks everyone for coming. My name is Sergey, and I work as an engineering lead in Mobimeo. And today I would like to talk about our journey in building our own GTFS-Realtime data processing pipeline. So I would like to start my talk with framing the problem Mobimeo is aiming to solve, give some short intro into public transport data domain, and state the challenges and specific requirements we had to deal with, justify the choice of stream processing approach, and share the big picture of our data processing architecture and the role of Kafka ecosystem in it. A few words about the Mobimeo. This is the tech company of Deutsche Bahn, delivering mobile digital mobility as a service solutions to mobility providers. Our goal is to make access to daily mobility as easy as possible, and we believe in connected mobility, but often for the user, all new modes of mobility and transportation are like intransparent puzzle. With our digital solutions, we want to make easier to find the best mode of transportation and make daily commuting effortless to the customer. We focus only on the day-to-day urban transport, not on the long distance travel, as we believe that this customer group has very specific needs. And our overall target is to change how city move and to reduce the number of cars in the city. As a venture of Deutsche Bahn, mobility is part of our DNA. We combine the industry expertise of a leading mobility company with the agility of technology startup. We were founded in 2018 and already have around 170 employees from over 39 nations. Officially, we are located in Berlin-Kreuzberg, but currently mostly working from home. As part of our business, we focus on partnerships and developing digital products together with our partners in the colors of the brand, so-called white label solutions. Our offer is flexible. The mobility company can choose a complete app with brand customization or seamlessly integrate individual models into existing apps. For example, in Berlin, we have a BVG as a customer who have integrated our live navigation feature in the Far Info app. Also, S-Bahn Berlin is our customer, but they got the full-fledged white label solution. We only focus on what the most important information in our apps. They are intuitive and have a clean design. Through extensive user feedback and analysis, we know which features the user really needs. And as we are talking about the essential capabilities in routing, in navigation, or in transportation apps, the routing capabilities are essential part. When the user searches for a route from A to B, he expects to get very accurate and relevant route suggestions. Routing is a very complex engineering challenge itself, where data plays a critical role. Its freshness, accuracy, and coverage are key success factors for finding an optimal route. Routers that operate on stale data are useless, as in reality, buses are getting stuck in the traffic jams, trains get cancelled due to the union strikes, and normal operating schedules are often changed to planned construction works or completely unplanned challenges. So any router should use not just a pre-planned operational schedule, but also receive timely updates about the current situation in the reality. There is plenty of data models used to exchange public transport information nowadays, like Transmodel, NetXC, to name few. But the factor most commonly used is GTFS open data format proposed by Google in 2005. The general transit feed specification defines a common format for public transportation schedules and associated geographic information. GTFS feeds let public transit agencies publish their planned transit data and developers to write applications that consume the data in interoperable way. It models, among many entities, stop locations, bus routes and rail alignments, schedules, demand-responsive transit, fares, service alerts, and so on. Update frequency of GTFS data varies from a couple of months to a couple of days, and also includes all information about planned deviations from the normal schedule, such as construction works. GTFS-Realtime, on the other hand, is a feed specification that allows public transport agencies to provide real-time updates about their fleet to application developers. It's essentially an extension to the GTFS specification. GTFS-Realtime was designed around ease of implementation, good GTFS interoperability, and a focus on passenger information. A GTFS real-time feed lets transit agencies provide consumers with real information about disruptions to their services, stations got closed, lines not operating, important delays, etc. Location about their fleet and expected arrival times. There are many things in reality which might happen that should be taken into consideration and transparently displayed to the user when he's planning his trip, such as cancellations or additions of the trips, change of the pattern, sequence change of the mode of transportation, vehicle equipment, platform changes, schedule deviations. It's not only the case that the transport is delayed, but sometimes it might be departing earlier. There might be traffic jams affecting the current schedules, and the vehicle capacities, passenger loads becoming more and more important topic, and other attributes as well. All of these scenarios could be captured and transmitted as GTFS real-time updates. Mobimeo routing engine is based on the GTFS-RT specification. However, the real-time data supplier we integrated with is unfortunately based on the German variation of series specification. So we had to solve a problem of translating data from this format to the GTFS-RT. We had to deal with many different challenges during this implementation phase, which I would like to explain further. So the data we received from supplier is similarly to the GTFS, and it has two parts, reference and real-time data. Reference data represents currently planned trips and getting delivered in batches roughly 4 hours before the public transport vehicle departs from the first stop on its route. This data already includes all planned deviations from usual operating schedule and represents a full trip as it should be in the future. Real-time, in contrast, represents only deviations from previously transmitted data. It assumes that the processing of this data should be in order and only on top of the reference data. But it also can contain a full trip information. For example, when there was a previously submitted mistake and there is a need for correction. Naturally, those trip update messages are different in many regards and have specifics in their processing. For example, if you are comparing plant and the real-time updates, plant updates frequency are very rare. It's once per X hours, and the real-time updates are very frequent, every minute or more often. The volume of data is also different, as plant updates are updates about all the trips which will happen in the next few hours, and the real-time updates are only about the trips which are changing and which is currently running. So the volume is much smaller here. The verbosity of the information inside the individual messages are also different. With the plant updates, we have a full information about the trip, and in the real-time updates, it's only incremental data and only the things which are getting changed. The nature how this data is arriving is also different. The plant data is arriving at once as a one batch, and the real-time is basically non-stop arriving. Due to the difference of this, due to the different requirements to process this data, we can also define the SLAs and define how this data should be processed, like what is the processing latency. Can we postpone processing some planned data, and whether the real-time data should be the critical and should take over the processing of the planned data. So this is the approach to follow. They all deliver to the same interface and the same integration with the data supplier. On this slide, you can clearly see some distinct patterns how data arrives in terms of volume and frequency. With red arrows, I'm highlighting moments when the reference data is transmitted. It happens every 4 to 5 hours, as clearly seen, and much larger in the size. Updates, therefore, are hugely disproportionate, and we have to address this challenge explicitly. As previously mentioned, there is some rules which should be enforced when processing those updates, like we have to deal with the situation when the information about the current and future trips are mixed. Planned trips should be processed first because they are setting the initial trip state, and real-time updates are only partial data and should be applied in order on top of each other. And there is another business logic we need to implement, the delays extrapolation. So I will talk about this in a second. To prevent unnecessary data traffic, measures are introduced to avoid the transmission of redundant information. And this is particularly important about the delay information. To reduce transmitted data volume, data supplier reports as part of update message only those stops at which the delay has changed. And the schedule information system should assign the last reported delay to all stops along the pattern until the next reported delay is received. So in this example, the real-time update would contain only information about the first and the third stop on the trip route, and our processing logic should extrapolate the delay between the first stop and the third stop, which is 2 minutes, and then from the third stop onwards until the end of the journey as 1 minute. And the follow-up trips is going to be on time, because there is no update about this trip we received as part of the real-time information. Another great engineering challenge we had to solve was in translation of incoming information to the format our router can accept. It turned out to be a very complex and resource-heavy task, as none of the identifiers in the incoming data were matching corresponding entities in the GTFS feed. So we had to build a lot of supporting backend systems to support data matching, and we used fuzzy logic to find similarities in the data sets and correlate them by modality, line name, sequence of stops, departure and arrival times, and apply other heuristics to be able to match the trips between the GTFS static data and the feed we are getting from our data supplier. GTFS information is planned static schedule data, but because it also contains all planned schedules, exceptions, or deviations due to construction works, for example, it is always essential to keep the latest version of it. The challenge with this data set is unstable IDs. So, for example, exactly same trip would have unique identifiers assigned across different feed versions for the same region from the same provider. And in order to have uninterrupted operation of the router, what we need to do, we need to support data conversion to multiple GTFS feeds versions on the same time simultaneously. GTFS feeds updates are usually updated not so frequently, but in the current situation, we got a new update every couple of days. So, like, if you will consider all of these challenges and specifics, stream processing paradigm seems to be fitting perfectly the engineering task I have described so far. Before stream processing, data was often stored in a database, a file system, or other form of mass storage, and applications would typically periodically run queries on top of the data over the batches and compute some logic, execute some computational logic over the data as needed or when requested. Applications were fetching parts of data themselves and maintaining their state externally on their own. Stream processing turned this paradigm around. The application logic, analytics, and queries exist continuously, and data flows through them continuously. Upon receiving an event from the stream processing application reacts to that event. It might trigger an action, update an aggregate or other statistic, or remember that event for future reference. Streaming computations can also process multiple streams jointly, and each computation over the event data stream may produce over event data streams, may produce over other event data streams. Conceptually, stateful stream processing brings together the database or key value store tables and event-driven reactive application or analytics logic into one highly tightly integrated entity. If you are considering what are the benefits of the stream processing, I would like to name a few. Applications and analytics reacts to the events instantly. There is no lag time between event happen, insight derived, and the action is taken. Actions and analytics are always up to date, reflecting the data when it's still fresh, meaningful, and valuable. Stream processing can handle data volumes that are much larger than other data processing systems, and the event streams are processed directly, and only a meaningful subset from the data is persisted. Stream processing naturally and easily models the continuous and timely nature of most of the data. This is in the contrast to the scheduled or like batch queries and analytics on static resting data. Incrementally computing updates rather than periodic recomputation of all data fits naturally with the stream processing model. The most naive approach will be to implement stream processing yourself. You have an unbounded incoming stream of data. You implement a consumer to read from that input, apply some logic or transformation, and push results to some destination. Sounds simple, right? Unfortunately, that simplicity has a cost. When you will need to do more complex manipulations with data streams, you will have to deal with many non-trivial issues, such as what if you need to join multiple streams? Or your data stream consists of data in arbitrary order? Or you need to apply a stateful operation? How to recover from failure, how to scale processing, and so on. So you have to deal with many things in real world when processing the data, which are actually already got successfully solved. In Mobimeo, we decided to build a stream processing pipeline on top of the Kafka ecosystem. Kafka combines 3 key capabilities, so you can implement your use cases for event streaming end-to-end with a single battle-tested solution. First, you can publish, subscribe streams of the events, including continuous import-export of your data from other systems. You can store streams of events durably and reliably for as long as you want, and you can process streams of the events as they occur or retrospectively when you like. And all of this functionality is provided in a distributed, highly scalable, elastic, fault-tolerant, and secure manner. Our Kafka ecosystem consists of Kafka Core, Kafka Streams, Kafka Connect, and the Schema Registry. Kafka Connect is a connector API to create reusable producers and consumers that consume or produce streams of events from and to external systems and applications so they can integrate with Kafka. For example, a connector to AWS S3 might be used to export data into the data lake. That's what we are using, for example. In practice, you typically don't need to implement your own connectors because the Kafka community already provided hundreds of ready-to-use connectors. The Schema Registry is a Confluent tool that manages schemas versions and compatibility, as we are using our binary format for the Kafka records. And Kafka Streams is a streaming API to transform, aggregate, and process records from a stream and produce derivative streams. Input is read from one or more topics in order to generate output to one or more topics, effectively transforming the input streams to the output streams. As our pipeline is heavily based on the Kafka Stream API, therefore I would like to touch this topic in more details. Kafka Streams is a very powerful library which takes away a lot of headache. It perfectly fits a distributed, horizontally scalable production environment. You can do it is both stateful and stateless processing. It supports handling data which is arriving not in an order. You can do very complex operations such as windowing, joining multiple streams, and aggregation. Kafka Streams supports time-based aggregation, enabling it to answer questions such as how many events occurred in the last 5 minutes, what was the total value of orders placed each hour today, and how many minutes have elapsed between the customer actions. You can have a choice and use either the internal time step of a message or an arbitrary field from the message payload when performing time-based aggregations. And you can use transactional processing, as Kafka Streams fully support exactly one semantics and are fault tolerant. Technologies such as Storm, Spark, Flink, or Samda would require in the similar scenario or setup a dedicated cluster to execute stream processing. Kafka Streams, in contrast, does not require a dedicated cluster except of Kafka itself. The library itself has no external dependencies and very lightweight. There is a Scala wrapper provided to make the Java APIs more usable in Scala through better type inferencing, enhanced expressiveness, and lesser boilerplate. Real-time processing might be a critical requirement for many business applications when micro-batching is not an option. Is your application sensitive to the processing latencies? Consider for exchange example when you don't want to get your currency exchange rates be outdated. Kafka Streams employs one record at a time processing to achieve millis latencies, and in the same time is designed to handle out of order or late arrival of the data. The library itself is very developer friendly. It provides 2 flavors of APIs. There is a high-level DSL API, which is similar to Java 8 Stream API, and low-level processor API, which is giving much more granular control over the internal state stores, for example. The app with this library can be executed locally in Docker container, run inside Kubernetes cluster, and there is no overhead of setting up and maintaining many moving pieces. And what is also very important, to test a Kafka Stream application, Kafka provides a test-util artifact that can be added as a regular dependency to test your code base. On this slide, you will see a big picture of architecture we have built. Data from the external supplier is received in XML form. Injection system is parsing XML, splitting payload to the individual messages, and then syncing them for further processing in Kafka topic. We operate data in Avro format. Therefore, all consumers and producers are connected to the schema registry, which keep records of all registered Avro schemas. We do persist raw and processed data in our data lake. For that, we use Kafka Connect, which syncs data to the S3. In blue, I have highlighted our streaming apps, which are working on the high level as follows. Aggregator consumes trip update that does not contain any GTFS data. The messages might contain data about a full trip or just part of the trip. Then aggregator gathers additional metadata and generates a new state of the full trip by applying any partial updates and also enriching data to simplify further processing. Aggregator also evaluates if the trip update is urgent or not and publishes the new full trip information. Converter consumes this update. It checks about the trip update urgency. We have dedicated instances to handle important and others for non-important trip updates. Conversion operation takes place and GTFS-RT message is pushed to the outgoing topic from where it will be consumed by the routing engine. On this slide, you can see an example of using high-level API to set up stream aggregation. What happens here is that we compute the full current state of the trip based on the planned or initial state, and then applying all incremental data updates which are consumed from the input topic. Before and after aggregation, we record timestamps and computing the latency processing metrics. Result of aggregation is most up-to-date enriched trip information, which is synced to the output Kafka topic for the further processing. In order to process messages marked as urgent as quickly as possible, we have implemented two flavors of the streaming apps. Fast converters are only processing urgent messages which are marked for immediate processing. This deployment have more resources allocated and uses a lot of pre-cached values. Slow converters are handling not urgent messages. It performs heavy lifting and populating caches. So to avoid overloading upstream backend system, the processing is spread over time. That's why we don't really want to have as many slow converted instances as fast one, because it will abuse other parts of the backend systems. Those apps are sharing exactly the same processing logic and differs only on the configuration side and deployment parts. To resolve data against multiple versions of GTFS feeds, separate deployment with dedicated configurations are rolled out, but the code itself is shared. The router engine can filter the GTFS-RT stream by selecting only relevant update messages. In this snippet, you can see demonstration of how the conditional processing of the message depending on the application configuration. We are using FlatMat to resolve a single incoming message to 0 or more GTFS-RT messages which are synced at the end to the destination topic. And then the router will filter based on the feed ID which message he's going to consume. That's all what I wanted to share with you. Thanks a lot for your attention. Also, I would like to encourage you to download our app to be up to date with any public transport disruption in Berlin. In this app, we also feature route subscription function, so you will get all updates about any upcoming changes to your preferred routes. Thank you so much.
Thank you guys for your talks and taking the time. Thank you all for attending and coming to the meetup.